Good morning, students. Welcome to the class on spectroscopy. Today we will discuss about carbon 13 NMR spectroscopy. We know there only the nucleus which is having non-zero nuclear spin. They are only NMR active. Carbon 12, it is having a zero nuclear spin, so it is NMR inactive. Whereas carbon 13, it is having a nuclear spin of half, so that means it is NMR active. It is NMR active, right? So we can study about the carbon 13 NMR spectroscopy. But the points to be noted is the carbon signals are 6,000 times weaker than proton signals. The carbon signals are 6,000 times weaker than proton signals. There are two reasons for this. One is that the gyromagnetic ratio. Gamma for carbon is 4 times lesser than gamma for hydrogen, right? So we know the frequency is uh, uh, is directly proportional to gamma value. So gyromagnetic ratio. Another important point is carbon 13 availability. Carbon 13 is only 1.1% available. Carbon 12 is 100% available. Carbon 13 is only 1.1% available. Whereas proton is 100% available. So that is why we are getting a strong signal. That means if you take a molecule which is having 6 protons, all 6 protons will exist. But if you take a molecule which is having 6 carbons, out of the 6 carbons, how many carbons will be carbon 13? Say for example, if you have 100 carbons, only one carbon will be carbon 13. If you take 6 carbons, even carbon 13 may not exist in this molecule, right? So that is why, due to the availability and low gamma value, carbon signals are generally very weaker than proton signals. So to rectify that, what we will do, we will do more scanning. Proton NMR we can get within 2 to 3 minutes, but for carbon 13 we need to go for 5 to 10 minutes. And next important, we will take more compound. We will take more compound. Generally, for proton NMR, 1 to 2 milligrams is enough. 1 to 2 milligrams of compound is enough. But for carbon 13, we need around 10 milligrams. Or if the molecular weight is high, then we need even some more high amount of compound. So to rectify the weak signal of carbon 13, what we will do? We will do more scanning. That means we will take the spectra for about 5 to 5 minutes. Then we also use high compound. So for proton only we need 1 to 2 milligrams, whereas for carbon 13 we need 10 milligrams of the compound. And not only that, when you look at the frequency of carbon 13, is 1 by 4 times of frequency of proton. Why? Because the carbon 13 gamma is 4 times lesser than gamma of proton. So that is why the frequency of carbon 13 will also be 4 times lesser than proton. For example, if we were doing a proton NMR spectrum on a 300 megahertz instrument, then the same instrument, we are not changing the magnetic field, but the same instrument, when we do it for carbon 13, it becomes only 75 megahertz. It becomes only 75 megahertz. Why? Why? Because the gamma of proton is 4 times larger than carbon 13. So if you were given the frequency in protons and if you were asked to calculate the frequency in carbon, then what we will do? We will divide the frequency of proton with 4 so that we will get the frequency of carbon. Similar to proton NMR, carbon 13 NMR will also give signals of carbons. Similar to proton, here also we will observe only non-equivalent, chemically non-equivalent carbons. Chemically equivalent carbons will give one signal, chemically non-equivalent carbons will give different signals. Now we will look at the delta scale for C13 NMR. Generally, we will have high delta values in case of C30. A methyl group will generally appear at 8 to 30 ppm. Methyl group which is attached to an sp3 hybridized carbon. A methylene group will appear at a little large delta value. Then a tertiary or quaternary carbon will appear little large delta value. So with increase in substitution, we will increase the delta value. If a more electronegative atom is directly attached to the carbon, then because of its effect, it will have high delta value compared to these methyl groups. For example, if we have nitrogen, it will be between 30 to 65. If we have oxygen and carbon, it will be between 40 to 80. If we have chlorine, it is 35 to 80. And if we have bromine, it is 25 to 65. It is based on their electronegativity differences. C triple bond C is generally appear between 65 to 90 ppm, whereas C triple bond N appears between 100, 110 to 140, 110 to 140. C double bond C appears between 100 to 150. C double bond C appears between 100 to 150. Yeah, the position of this is maybe wrong. Please write it here. Then aromatic carbons. Aromatic carbons will appear also appear between 110 to 175. Aromatic carbons will also appear from 110 to 175. Then we will have carbonyl carbons. Among the carbonyl carbons, carboxylic acids, esters, and then amides, anhydrides. They will appear between 155 to 185 ppm. As I have shown here, these two carboxylic acids and esters, they will appear towards the 180 side, these two amides and anhydrates, they will appear towards 160. So that means among these four systems, esters and acids will have high delta, amides and anhydrates will have low delta. And finally, we have aldehyde carbon and ketonic carbon, which generally appears between 185 to 220. Aldehyde carbon and ketone carbon will appear between 185 to 220. Among these two carbonyls, aldehydes and ketones, ketones have high delta, aldehydes have low delta. So ketones will appear around 220, whereas aldehydes will appear around 190. When we look at the delta values and when we compare it with the proton values, proton delta values are 1 to 10, whereas for carbon 13 the values are 0 to 220. That means the carbon 13 values are around 20 times larger than proton. The delta values for carbon 13 are 20 times larger than proton. Why they are giving such a high delta value? One thing we can clearly say, in case of protons, if it is having some substitution will be on carbon but not on hydrogen. So that means protons are not directly influenced by the substitution or anisotropy effects, whereas carbon is directly attached to withdrawing groups or releasing groups, so it is directly influenced by the substituents. So because it is directly influenced by the substituent, it will have large frequencies compared large delta values compared to proton. When we look at the factors influencing delta values of carbon 13, it is same as proton NMR spectroscopy. The influencing factors on delta are electronegativity, hybridization, and anisotropy. It is same as proton NMR. Of course, the influencing factors are same, but the difference in large delta values is due to the direct influence. Proton is not directly influenced by the substituents, whereas carbons are directly influenced by the substituents. So that is why they will exhibit large delta values compared to protons. Now we will calculate the lambda values on alkenes. How do we take these things? Here the base value for alkene, that means either this carbon or this carbon. The base value for alkene carbon is 123.3 ppm. 123.3 ppm. For example, if you want to calculate delta value for this carbon, how these substituents will influence this delta value. So I'll give a table. Substituent y x. What does it mean? Y means a substituent which is directly present on this carbon. X means a substituent present on the other alkene carbon. Y means substituent present on the alkene which we are calculating. X means the substituent which is present on the other alkene carbon. Okay, we are not we are not worrying about the other alkene carbon, right? In this case, we are calculating the frequency or delta value for this carbon, right? If we have hydrogen, it doesn't have any influence. If we have methyl group, if methyl is present on carbon which we are trying to calculate the delta value, we need to add 12.9. If it is present on the other alkene carbon, then we will subtract 7.4. Similarly, if ethyl group is there on the carbon which we are calculating the delta value, we need to add 19.2 to the base value. If it is present on the other alkene carbon, then we will subtract 9.7. If we have N propyl group, we will add 15.7 if we are studying about the direct carbon. If it is on the next alkene carbon, we will subtract 8.8. Similarly, for isobutyl, it is 22.7 minus 12.0. For tertiary butyl, it is 26.0 minus 14.5. For a pH group, it is 12.5 minus 11. So when we look at these substituents, if they are present on the carbon which we are calculating delta, we will add. If it is present on the other alkene carbon, then we will subtract. There are only two exceptions, N-propyl and tertiary butyl. See, the shortcut is, if you have methyl group, add 10 or subtract 10. If it is on the carbon which we are calculating delta, just add 10. If it is on the other alkene carbon, subtract 10. Ethyl, add 20, subtract 10. N-propyl 15, 10. That is why I mean star mark. It is exception. Isobutyl 20, 10. Okay, don't remember the exact values. Just add 20 if it is on the direct carbon. If it is on the other carbon, subtract 10. Tertiary butyl 25. So that is why I have given a star mark. 25, 15. Add 25 or subtract 15. Phenyl group is similar. Add 10 or subtract 10. Methyl and phenyl, add 10 or subtract 10. All other, ethyl, isobutyl, add 20 or subtract 10. N-propyl, add 15 or subtract 10. Tertiary butyl, add 25 or subtract 15. You just go for some general value. Okay, don't remember each and every value. It is highly difficult. Similarly, if we have chloromethyl group, add 10 or subtract 5. Bromomethyl, add 10 or subtract 5. Iodomethane, add 15 or subtract 5. So this is the only difference. If it alcohol, then also add 15 or subtract 10. Don't remember this 10.9, 14.2. Add 10 for chlorine, bromine, chlorobromomethyl or subtract 5. Add 15 for iodo or alcohol or subtract 5. 5 or for oxygen, you can go for 10. It's not a problem. Okay. So just take these shortcuts. Don't remember the exact values. Then carboxylic acid is an exception where we will add 5 and 10. Carboxylic acid is an exception where we will add 5 and 10. We will add both times, we will add. If you have NO2 group, add 22 or subtract nothing. Okay. So it is similar to these alkyl groups. Add 20 or subtract nothing. Add 22, add 20 or subtract nothing. Similarly, if we have OCH3 group, add 30, add 10, subtract 40. OCH3 add 30 or subtract 40. O acetate group add 20 or subtract 30. I'm sorry. For OCH3 add 30 or subtract 40. For O acetate add 20 or subtract 30. Okay, you just remember the round figures. Now we will look at nitride, aldehyde, ketone, acid chloride and silicon groups. When we have these groups, nitrile is an exception. Nitrile is an exception where we will subtract 15 or add 15. It is opposite way, right? If it is on direct carbon, because it is strong withdrawing, we will subtract 15. If it is on the other carbon, we will add 15. For aldehydes, add 15 or subtract 15. Aldehyde, add 15, subtract 15. Ketone, add 15, subtract 5. Ketone, add 15, subtract 5. Acid chloride, add 10. I'm sorry, these are all additions only, right? These are all additions only. So yeah, these groups are only additions, no subtractions. Only exception is nitrile group. So acid chloride add either 10 or 15. Trimethyl silyl group add 15 or 5. So in this case only additions. Nitrile is the only exception. If you have nitrile, subtract 15 or add 15. Aldehyde, add 15 wherever it is, add 15. Ketone, add 15 and 5. 15 and 5. Acid chloride, 10 and 15. 10 and 15. Trimethyl silyl, 15, 5. So these are all similar groups, right? So that is why I have grouped all these together so that we can easily remember them. Now we will see halogens. Halogens. For fluorine, add 25 or subtract 35. For chlorine, add 25 or subtract 35. Similarly, for iodine, it is a reverse way. Subtract 40 or add 5. Subtract 40 or add 5. So these are only high values. Chlorine and bromine, they are having very low values. If you want to subtract, you just subtract 5. If you want to add, just ignore it. Bromine, bromine is subtract 10 or leave it. How do we remember them? We need to remember fluorine and iodine only. Fluorine, add 25 or subtract 35. Iodine, subtract 40 or add 5. Chlorine and bromine, just ignore it. Okay. Or what we need to do? Chlorine, add 2, subtract 5. Bromine, subtract 10 or leave it. Okay. For chlorine, we need to subtract 5 if it is other carbon. For bromine, we need to subtract 10 if it is the same carbon. Okay. So this way we can easily remember the values. We will look at one example. We will try to calculate it. So this is first carbon, this is second carbon. Say for example, when we want to calculate for first carbon, base value is 123.3. Then we have bromine on this. When we have bromine, I said subtract 10. When we have methyl, subtract 10. So it will be around 103.3. Exact value is 107.3. So you will get similar values. You don't need to worry. Similarly, for C2, 123.3 is the base value. We have methyl. So add 10 because methyl is on directly on this carbon. Bromine is on the other carbon, just leave it. So we will get 133.3. Exact value is 135.3. So we will get similar values. So this is enough for exam. For example, I will give one more problem. COOH. This is 1, 2. When you want to calculate first carbon, base value is 123.3. We have a carboxylic acid. Carboxylic acid is an exception. Add 5, add 10. Then methyl group, subtract 10. So 128.3. Exact value is 120.9. For C2, similarly, if we do that, 123.3, methyl is there, add 10, carboxylic acid is there, add 10, it will give 143.3, exact value is 146. So we can have comparable values so that we can easily choose the answer. Okay, in the exam they don't confuse you.